Good morning, everyone. My name is Steven Joseph Phoebe, S7ECA, roll number 27. I'm going to take seminar on the topic Underwater Wireless Sensor Networks. I have prepared the slides under the guidance of Assistant Professor Mr. Srish PR, Department of Electronics and Communication Engineering. Moving to the contents page. First we have introduction, then wireless sensor networks, then working of wireless sensor networks, then underwater wireless sensor networks, then working of underwater wireless sensor networks, then its communication methods, then architecture, then routing protocols of underwater wireless sensor networks, then depth-based routing of underwater wireless sensor networks, then pressure-based routing, then location-based routing, then clustering-based routing, then challenges, then limitations, then conclusion, and last references. Moving to the introduction. 75% of Earth's surface is covered with water in the form of rivers, canals, seas, and oceans. Plenty of these underwater resources remain largely unexplored. Successful underwater exploration relies heavily on technological advancements. Underwater wireless sensor networks are a specialized subset of wireless sensor networks. These networks consist of a collection of autonomous underwater sensor nodes that communicate with each other to collect, process, and transmit data from the aquatic world. Moving to the next slide. Wireless sensor networks. What is a wireless sensor network? Wireless sensor network is an infrastructure-less wireless network that is deployed in a larger number of wireless sensors in a ad hoc manner that is used to monitor the system physical or environment conditions. It has sensor nodes that manages and monitors the environment in a particular. They are connected to a base station which acts as the processing unit. The base station in wireless sensor network system is connected through internet to share data. Here is a figure showing wireless sensor networks. The sensor nodes are deployed in a region called the sensing region. The sensor nodes are then connected to the base station. The base station then is connected to the internet where the user can access the data. Moving to the next slide, working of wireless sensor networks. The first step is deployment of sensor nodes. These nodes are deployed in the area of interest. The sensor nodes are typically small autonomous devices equipped with sensors for data collection. The next step is data sensing. Sensor nodes continuously monitor their surrounding using the sensors they are equipped with. These sensors can measure various parameters like temperature, humidity, light, pressure or motion, etc. The next step is data collection. Sensor nodes collect data from environment at regular intervals or in response to specific events. Data collected can be in the form of analog or digital signals. The next step is wireless communication. Sensor nodes are equipped with wireless communication capabilities, allowing them to transmit data to other nodes with, or within the or to other nodes within the network. They may use wireless protocols such as Bluetooth, Wi-Fi, etc. The next step is data transmission. The collected and processed data is transmitted from one sensor node to the another sensor node. The data can be sent directly to a central base station or relayed through intermediate in a multi-hop fashion. The next step is routing. Routing algorithms determine how data travels through the network. These algorithms aim to optimize factors such as energy efficiency, data reliability. They ensure the data reaches its destination efficiently. The next step is base station. In many wireless sensor networks, there is a central base station or a sync node. This node collects data from the sensor nodes and acts as a gateway to external networks or applications. The next step is energy management. Energy conservation is crucial. The energy sensor nodes are powered by batteries. They use techniques like duty cycling or sleep mode and these are used to increase the node lifespan. Duty cycling means periodically turning on or off the sensor nodes. The next step is security. To protect data from unauthorized access or tampering, it implements various measures like data encryption, intrusion detection, and authentication. The next step is scalability. Wireless sensor networks can scale to accommodate varying numbers of sensor nodes, making them adaptable for different application requirements. The next step is real-time monitoring. It enables the sensor node and the wireless sensor networks enables real-time monitoring of physical phenomena or environment condition. The next step is adaptation. Sensor nodes and sensor nodes and the network act as a whole to adapt to the changing conditions, including node failures or reconfiguration to ensure continuous data collection and communication. Moving to the next slide, underwater wireless sensor networks. Underwater wireless sensor networks are a specialized subset of wireless sensor networks designed to operate in challenging and dynamic underwater environment. It's a figure showing underwater wireless sensor network. Moving to the next slide. Working of underwater wireless sensor networks. The first step is node deployment. Sensor nodes are placed in the underwater environment of interest. Either these nodes are either anchored or attached to structures or mobile. The second step is data sensing. Sensor nodes are continuously monitor the underwater, collecting they collect data on the parameters like temperature, pressure, or the acoustic signal using the sensors they are equipped with. Third step is data processing. The data is processed. It involves noise reduction and data aggregation. The nodes collect data from the underwater at regular intervals or in response to specific events. The next step is acoustic communication. Underwater wireless sensor networks use acoustic waves for communication due to the limited propagation of radio signal in the underwater. The next step is data transmission. Nodes communicate via acoustic signals in the underwater. The next step is localization. Accurate node positioning is essential for precise data collection and routing. The next step is routing. The routing algorithms determine how data travels through the network. These algorithms aim to optimize factors such as energy efficiency and data reliability. They ensure the data reaches its destination efficiently. The next step is data aggregation. Aggregating data from multiple nodes, it reduces redundancy and conserves energy during the transmission. The next step is base stations or buoy communication. Surface buoys or autonomous underwater vehicles serves as communication hubs between underwater nodes and terrestrial networks. The next step is energy management. Nodes use energy-saving techniques such as duty cycling or sleep nodes to extend the battery life. Duty cycling means the sensor nodes are periodically on or off. The next step is security. The sensor nodes implement security measures to protect data and network from unauthorized access and tampering. They use measures like authentication, encryption, and intrusion detection. The next step is challenges. It faces high pressure corrosion by falling and variable water condition and impacting the node performance. Moving to the next slide, communication methods. The underwater wireless sensor networks commonly used to communication methods. They are acoustic communication and optical communication. Moving to the next slide, acoustic communication. Acoustic signals are the most means of communication in the underwater. The sensor nodes use underwater acoustic waves to transmit data to other nodes or to the surface stations. Acoustic signals can travel over long distances but at a lower data rates. Here is a figure showing the acoustic communication. Moving to the next slide, optical communication. Optical communication involves the use of light signals for the data transmission. While it offers high data rates, it is limited to shorter distance and clear water communication. It's a figure showing optical communication. So we can say in acoustic communication, the acoustic signals can travel over long distances but at a lower data rates. But in optical communication, it offers high data rates, but it is limited to shorter distance. Moving to the next slide, underwater wireless sensor network architecture. The common underwater wireless sensor network architectures for designing the underwater wireless sensor network applications are one-dimensional architecture, two-dimensional UWSN architecture, three-dimensional UWSN architecture, and four-dimensional UWSN architecture. First, we discuss about the one-dimensional UWSN architecture. It refers to a network where the sensor nodes are deployed autonomously. Each sensor node is a standalone network itself, responsible for sensing, processing, and transmitting the information to the remote station. In one-dimensional underwater wireless sensor network, the nodes can communicate using acoustic, radio frequency, or optical communication. Underwater wireless sensor network architecture designed for environments where sensor nodes are deployed in a linear or one-dimensional configurations such as rivers, canals, or pipelines. The characteristics are linear deployment, simplified topology, communication along the line. For example, in case of a river, the one-dimensional architecture deployed in a river for monitoring, sensor nodes are anchored or along the riverbed, extending from the upstream to downstream. Sensor node communicate with each other nodes. It analyze trends for pollution sources, monitor water quality, and access the river health. Applications of one-dimensional underwater wireless sensor network architecture, river and waterway monitoring, pipeline and subsea cable monitoring, underwater infrastructure and surveillance, agricultural irrigation, aquaculture monitoring, and underwater archaeological exploration. The next is two-dimensional underwater wireless sensor network architecture. It refers to a network where a group of sensor nodes are deployed in underwater. This group of sensor nodes are called cluster. Each cluster has a cluster head, also called the anchor node. Each clusters are fixed as they are anchored at underwater surface. Each member of the cluster gathers the underwater data and communicates it to the anchor node. Its characteristics are 2D deployment, complex topology, and multi-hop communication. The applications of two-dimensional underwater wireless sensor network architecture are marine life monitoring, coral reef monitoring, underwater archaeology, underwater agriculture, underwater mapping and navigation. Three-dimensional underwater wireless sensor network architecture. In this type of network, the sensors are deployed in underwater in the form of clusters and anchored at different depths. There are three communication scenarios in this architecture. The first is inter-cluster communication of the nodes at different depths. The next is intra-cluster sensor to anchor node communication, and the third is anchor beyond node communication. Its characteristics are 3D deployment, complex topology, multi-hop communication. The applications of 3D architecture and the three-dimensional architecture, oceanographic research, marine biology and ecological monitoring, marine and shipwreck exploration, oil and gas industry, seabed mapping and geology, deep sea exploration. Four-dimensional underwater wireless sensor network architecture. The four-dimensional underwater wireless sensor network is designed by the combination of fixed underwater wireless sensor network, that is a three-dimensional underwater wireless sensor network, and a mobile underwater wireless sensor networks. The mobile underwater wireless sensor network consists of remotely operative underwater vehicles ROVs to collect data from the anchor nodes and relay the data to the remote station. Or ROVs can be autonomous submersible robots, vehicles, ships, and even submarines. Its characteristics are 3D space deployment and time dimension. The applications of 4D underwater wireless sensor network architecture. First is climate change and oceanography, then long-term ecological studies, underwater infrastructure lifecycle management, environment impact assessment for development projects, natural disaster prediction and response, research and rescue operations. Moving to the next slide. Routing protocols of underwater wireless sensor networks. Routing protocols in underwater wireless sensor networks are crucial mechanisms that enable efficient data transmission in the challenging underwater environment. These protocols determine how data is forwarded from source nodes to the sink nodes or intended destination, taking into account factors such as node location, depth, energy constraints, and communication conditions. Underwater wireless sensor network routing protocols can be categorized into depth-based, pressure-based, location-based, clustering-based, and more. First, we discuss about depth-based routing of underwater wireless sensor networks. It is based on the depth information of the underwater sensor networks, sensor nodes. Each underwater sensor node is equipped with a depth sensing capability. This capability allows the nodes to measure their own depth or the depths of the neighboring nodes. Its advantages are energy efficiency. It means it optimizes the consumption and chooses the path that require less energy and intensive communication. Improved communication reliability. It means selecting relay nodes with similar depths, which reduces signal attenuation, leading to the more reliable data transmission. The next advantage is enhanced data throughput. This routing leads to the selection of more efficient communication paths, resulting in higher data throughput. The examples are depth-based forwarding and depth-based shortest path. The next is pressure-based routing of underwater wireless sensing networks. It relies on the pressure information to make routing decisions. Sensor nodes are equipped with pressure sensors that can measure the water pressure at their current locations. Water pressure increases with the depth in underwater environments, so pressure sensors provide information about the depth of the node. The advantages are accurate depth information. This routing provides accurate improving precision of the routing decision in underwater. The next is energy efficiency. It optimizes the consumption of energy by choosing the path that require less energy. The next is depth compatibility. The nodes can select relay nodes at similar depth, reducing the signal attenuation and enhancing the communication capability. The next is location-based routing of underwater wireless sensor networks. It relies on the geographical positions of sensor nodes to make routing decisions. Sensor nodes are equipped with positioning systems like GPS or other localization techniques to determine their geographical coordinates underwater. The coordinates is expressed in latitude, longitude, and depth are used to identify the node's location within the underwater environment. The advantages are precision. It means routing decisions are based on the accurate geographical positions, leading to the precise data forwarding. The next is energy efficiency. It optimizes energy consumption by choosing the communication path which require less energy. The next is scalability. It means it is well suited for larger scale underwater wireless sensor network, and routing decisions are based on the node positions rather than the complex addressing schemes. The next is clustering based routing of underwater wireless sensor networks. It organizes sensor nodes into clusters to improve network efficiency and manages communication. The underwater wireless sensor networks is divided into clusters with each cluster typically having a cluster head. Cluster information can be based on various criteria such as geographical proximity, node energy levels, or other factors. The advantages are energy efficiency, scalability, and load balancing. The load balancing means the cluster head distributes the network traffic, preventing congestion and balancing network load. Challenges of underwater wireless sensor networks. First is unpredictable underwater environment. Underwater conditions are extremely unpredictable. The anonymous high water pressure, unpredictable underwater activities, and uneven depths of the underwater surface make it difficult to design and deploy underwater sensor networks. The next is intricate network design and deployment. Due to the unpredictable underwater environment, it is extremely difficult to deploy the network underwater, which works reliably and wirelessly. The current further technology allows the constrained communication, but it offers significant cost of deployment, maintenance, and device recovery to cope with the volatile undersea conditions. The next is a requirement of novel protocols of underwater wireless sensor networks. It means in underwater communication, the medium of communication is what, unlike air in terrestrial sensor networks. Therefore, the terrestrial sensor network communication protocols get void in underwater. The next is physical damage to the equipment. The sensors used in underwater devices are susceptible to the routine underwater challenges. For example, algae collection in camera lens and salt accumulation, decreasing the effectiveness of sensors and so forth. The next is low data rates. Radio frequency communications are not effective in underwater communication due to the medium effect on communication. Water absorbs as much of radio frequency energy, and hence only very short range communication is allowable using RF instead. Acoustic communication is used to transmit pulse signals and low fidelity information underwater. The next is cost. Finally, the energy requirements and the cost of underwater wireless sensor networks are highly compared to the high power and regular battery replenishing techniques are quite costly. Moving to the next slide, limitations of underwater wireless sensor networks. The available bandwidth is severely limited. The underwater sensors are prone to failures because of falling, corrosion, etc. The battery power is limited, and usually batteries cannot be recharged easily. The next is harsh environment conditions. And underwater environments are corrosive and can lead to sensor node degradation over time. At last, conclusion. In conclusion, we can say that underwater wireless sensor networks represent a vital tool for unlocking the mysteries of underwater realm, promoting environmental sustainability, and contributing to our scientific knowledge of Earth's vast aquatic environments. As these networks continue to evolve, their potential for transformative impact in underwater research and applications remain promising. Underwater wireless sensor network can be efficiently used for exploring underwater medium for various activities such as environment monitoring, water pollution, marine life monitoring, oil rig maintenance, and military application. These are my references. Thank you.